All right, folks. I want to discuss today a little bit of an introduction to transformations, which you already have, actually. You spent quite a bit of time in Algebra 2 doing these. We spent quite a bit of time in geometry doing these. Now, in geometry, we did it with geometric figures, okay, so triangles for the most part. But if you remember, it's shifting things left and right or up and down. We call those translations. It's reflecting over the x or y axis. I call those reflections. We do dilations in geometry. We'll call those stretches and compressions here in algebra. But everything that we've done for the last 2 or 3 years in regards to working with functions and even images and pre-images in geometry has been prepping us for being able to do this. And what it allows us to do is to essentially, if we understand what our parent functions look like, okay, and we kind of had this discussion 3 or 4 days ago, we're learning a handful of points off of each parent function and just committing those to memory or knowing how to generate those from the parent function rule can then allow you with these transformations to quickly develop the graph of any function you ever want to come across very quickly. Okay. So we've got the parent functions here. Now I'm not going to ask you to write all these down. It does make sense, I think, to have these understood. Okay. We've talked about all of them up to probably this exponential. Haven't talked about the logarithmic yet. Haven't talked about reciprocal very often or in much detail. And then below that, the trigonometric functions, we haven't really talked about at all. If you want this parent functions sheet, which I think it should be something that you want, if you go to section 2.6 on the website, scroll down, there's a red link here that says parent function PDF. I think that's the best thing to do is just download that, keep that, print it out, whatever you want to do. I've had some people asking me, talking to me about, where can I get more examples? Can we do more examples in class and that kind of thing? And my belief in teaching kind of these higher level courses, guys, is that I don't think it benefits you in the long run by sitting here and doing 10, 15, 20 examples, because you really only then learn how to do those 10, 15, 20 examples. Okay? I want to make sure that we understand collectively, holistically, the entire system of mathematics, so that I can give you an endless number of examples and you have an ability to attack each of those. Does that kind of make sense? So I am a huge proponent for not necessarily trying to get you guys to do what I do on the board. Does that make sense? In examples. I don't like that idea. I don't like the monkey see, monkey do philosophy, okay? Because you only then can do the things that you have seen. Where if we take the approach of trying to understand the concepts and the math a little bit deeper, okay, collectively, holistically, then you can do whatever you haven't seen, which is what the goal is. But if you are a person that needs maybe a couple extra examples, or maybe somebody discussing it a little bit differently, keep looking at this stuff. Okay, I think my resources a lot of times are underused. Okay, but there's a lot of stuff that's very intuitive here that if you mess around with it a little bit, you can gain a much deeper understanding of this information. Okay, so that's where that parent function PDF is. I just kind of want to jump into the first types of transformation. So transformation, by definition, means to change something, right? Okay. If I'm going to transform, I'm going to, in some aspect, change the way something is. Okay. So all of these things are transformations. Okay. Now there's a grouping of them. Okay. Every time that I want to do one transformation, there's kind of a counter transformation that can go with it. meaning that if I want to shift this thing upwards, okay, there's a counter shift that could take place, and that's shifting it downwards. Does that make sense? If I want to move it to the right, there's also the ability to move it to the left. If there's a stretching ability or a enlargement ability, if you think about dilations from geometry, then there should be a compressing or a reduction ability. Okay, so those are all important things to think about. Now, this text calls them vertical shifting. The math word is translation or translating. Okay, so you're probably hearing me say that more often than shift. Okay. But a vertical shift is exactly what it says. You're going to be taking your function, okay, you'll grab the entire function, and you'll move it all up or down, whatever value they ask you to do that with. Okay, so adding a constant to a function shifts its graph vertically. Okay, it's upward if the constant is positive, it's downward if it's negative. Okay, so if you guys remember how we deal with functions, then we'll start with y equals f of x. Okay, start with a function y equals f of x is what they're saying right here. So your y values are generated by some rule f of x. And I'm just going to use the arbitrary rule x squared. Okay, if I can, because I think we all understand what y equals x squared looks like. Okay, you can start with any function that's your favorite, but I think starting with linear functions, sometimes linear functions have kind of some uniqueness to them that you might not be able to see all these things taking place the way we think they should. But with x squared, if we deal with x squared, I think that's a good one to start with and use. So basically we're saying it's y equals f of x. Okay, some rule. So if I go y equals x squared, what that rule is doing, x squared is my f of x. It is generating me y values when I know what the x is. So if I know what x is, let's say x is 2, what's the y value that it gives me? 4. Okay? So that is what this here is doing. That notation says your y value is some rule f of x. Okay? And it's going to generate your y value. Okay? Well, if that's going to generate my y values, when I add something to it, doesn't that just increase my y values by that amount? So if I said that y equals x squared, and then I put plus some c on here, let's just put c right now. So if I chose x to be 2, you said you got back 4, right? That plus c then means you add that c amount to the 4. So let's say c was 3. You would take the 4 that you got back from the x squared rule, and now you'll add 3 to that 4. Now you got the ordered pair 2, 7. If I graph 2, 7, you will see that it is the point 2, 4 plucked off the graph and moved up 3 units. Okay? So whenever we're adding some constant to the entire function, okay, now it has to be to the entire function. Okay? It can't be just to the x before I square it. It has to be to the entire thing. Okay? So it'll be just an attachment of plus 3 or minus 3 or whatever. If it's plus, you're going to move it up. If it's minus, obviously you're going to subtract from your y values then, and it's going to slide things down. So I've got an applet here. Well, I had an applet. Let's go. I put these in after I copied the. There it is. And all these GeoGebras that I'm going to show you here are designed to target one transformation at a time. And they are under section 2.6 on my website. They're pretty easy to manipulate. and hopefully give us a real good understanding of what's going on. So what this does in that black box versus f of x equals x squared plus b, the b value, so I'm going to start with x squared being my parent function. The b value is then corresponding to that slider up top. And as I change that slider, it should actually change the function. Okay? So if I look right now, I've got my parent function x squared. Okay? Well, if I take, let's just look at a few ordered pairs on there. We know 0, 0 should be on there. We know 1, 1 is on there. We know 2, 4 is on there. And we can keep going, but let's just say we've got those three. Okay? Now, as I take this b value and add 1 to it, do you see that these parent function points, to get the points on the graph, don't I just take that one and add the b value to the y's? Does that kind of make sense? So take this one, I'll add my b value to the y, so it becomes 1, 2. Here, I'll add my b value to that y, so it becomes 2, 5. Does that make sense, everybody? And you can keep doing that, however many units I want to move that thing up. So this point right here, I'll just use this one because it's stuck on there. That one right there, if I look at that point, it is 1, 4. We'll go back to your parent function. Wasn't that point 1, 1 on your parent function? If I add 3 to that parent function's ordered pairs y value, I get 1, 4. So that's how we're going to transform these things. If I were to give you, ask you what does x squared minus 5 look like, my hopes are that the first thing you think about in your mind is the 5 points 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4 that show up on x squared. And if I'm going to remove 5, that means subtract 5 from each of those y values, and now you have an instant understanding of what x squared minus 5 looks like. It's a quick way to graph these functions instead of just arbitrarily setting up a t-chart and choosing independent variables and seeing what the y's give you. Okay. Can I get you to sign out on that computer? Now, so if I were to subtract, okay, it just means that we are going to remove values from the y's, okay? So again, from our parent function, we would have had this point right here, 1, 1, where my cursor is, okay? Well, if I subtract 3 from that y value, doesn't it put it down to 1, negative 2, where point A is down there on that curve? If you do that with enough points, you will be able to quickly generate x squared minus 3. Okay. Now, we can do this with all types of functions, guys. So what you can do in this applet is you want to do this with the x cubed. Okay. So I'll bring this back to a b value of 0. Okay. Acting funny. It's frozen. But I bring it back to the b value of 0, and then if I want to take that b and add 1 to it, it slides it up. Slides every one of those ordered pairs on that graph up. Okay, does that make sense to everybody? Okay. Now the idea is to remember what we're adding to. We're adding or subtracting to the entire function. Okay? And my thought is here, and this is the idea of saying, will we ever see enough examples? There is no chance that we could spend 15 minutes every single day going over example after example after example after example. And if you think about it, that would be a very, 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 very small set of examples in comparison to all the things that you could see. Okay? So the best thing is to understand this and realize, okay, regardless of what f of x is, because that's my rule right there, f of x. Well, if I make it square root, if I take this out and make it square root of x. What's going on? That was it. I don't know why that changed that. Okay, so if I type in square root of x, okay, it's a new function, but you see that it is being generated the same way as before. You're taking your f of x and you're removing 1 from it, so f of x would have had the point 0, 0 on it. Subtract 1 from the y, and it gives me that point right there. Okay? Square root of x would have had 1, 1 on it. Subtract 1 from the y, and it gives you that point right there. Okay? Square root of x had 4, 2 on it, so it had that point right there. Subtract 1 from it, it gives you that y. Does that make sense? Okay? So we should then be able to, no matter what f of x is, square root x squared, x cubed, 2 to the x, logarithmic base 2 of x, sine of x. It does not matter. It's some function that we've never even seen before. Probably your trigonometric, probably your logarithmic exponential. You've seen them, but maybe you haven't dealt a whole lot with them. If we started using those, or a reciprocal function, okay, it is going to do the same thing that it does to anything else, okay, any other type of function. You guys learned that maybe in Algebra 1, then if I start with the first line you graphed in Algebra 1, it's probably y equals x. And then you did y equals 2x, and y equals 3x, and y equals 1/2x, and y equals 2/3x. Okay, and they call those direct variation functions. And then you say, okay, well, what if I do y equals 2x plus 1? You had now a y-intercept, right? Well, if I compare y equals 2x and y equals 2x plus 1, the graphs are the same. It's just the 2x plus 1 is 2x. Vertically shifted 1 unit up. Okay? Questions on that? That's something we've maybe known, seen before, dealt with? Okay, good. Let's go to, yes?
This is going to be in the homework already assignment.
This is a new assignment.
I still don't understand that.
If we have time here towards the end. All right, so now I want to do horizontal shifting. Horizontal shifting. Okay, so this is moving left or right. Okay, this is a little bit different. And it looks a little bit different per function. Okay, so this will look a little bit different the way we write it for a quadratic. It'll look different than the way we write it for a square root, cube root, fourth root, something like that. So a root function. It'll look a little bit different for a logarithmic or exponential or a sine function. But if we remember the phrase, okay, something to the effect that you are going to add or subtract from your x before you run it through your function. Okay? Add or subtract to your x before you run it through your function. When I say run it through your function, I'm talking about the overall kind of governing function. Okay? So is it the square root function? Is it the cube root function? Is it the logarithmic? Is it the exponential? Is it a reciprocal? Are you doing something to the x before you basically go through your order of operations with those functions? Okay? So generically, they're going to say, okay, if y equals f of x, look down there and it says y equals f of the quantity x plus c. What that means to us is that we're going to add c to x before we then run it through our function. So you're going to take your independent variable, whatever you want x to be, and you're going to add the c that they're asking you to add. So if my x was like a 1 and my c was 3, instead of running 1 through my function, I'm going to run 1 plus 3 through my function instead. Okay? And what that does is it provides a movement left or right. And it's counterintuitive to what you think. When people think plus, they think move to the right, correct? Mm-hmm. Well, this is counterintuitive to that. So plus c is actually going to move it to the left. We have time tomorrow. We'll prove why it moves to the left when it's a plus and why it moves to the right when it's a minus. Okay? But right now, just maybe in your notes, write that movement is counterintuitive or opposite to the sign that is being used inside the quantity. Okay? So I've got down here just a generic f of x equals x squared. Okay? So if I look at f of x equals x plus c squared, okay, those parentheses, because of order of operations, tell me I need to add c to x before I run it through the governing function of that quadratic, before I square things. Does that make sense? Okay. If that's what's going on, then that is going to be a movement, in this case, left C units. Okay? Now it looks different for other functions. If I'm, all my power functions are going to be the same. So if it's like x plus 3 cubed, then that's going to take x cubed and move it 3 to the left. If I have f of x equals x plus 3 to the fourth, well, that's going to take x to the fourth and move it left 3 units. Does that make sense? So power function squared, cubed, fourth, fifth, sixth degrees, even first degrees, okay, are going to move it to the left. Okay. If we do square root, so let's say f of x, my original function f of x is equal to square root of x. Okay. To get that to be moved left or right, so this square root is the governing function, right? Then if I want to move it left or right, it's going to look like this. I want to add 3 order of operations there, which say whatever your x is, add 3 to it before we take the square root, right? So you're going to do something to your x before you apply that overall function. So that would actually move the square root function 3 units to the left. Okay? If you can remember that stuff, it's going to help us when we start seeing new functions throughout the remaining chapters, and the first thing they ask us to do is start transforming these. Well, if we remember, am I doing something to the x first? Am I doing something to the whole function? Will allow you to kind of manipulate and find those new functions, those new graphs, very quickly if we remember those statements about, am I doing something to the x before I run it through the function? And that's a horizontal movement. Okay? Just to show that, all right, so here we've got x plus c squared. Okay. Again, I'm just going to take that slider, and as I move it, plus 1, you see what the graph or the function looks like, and then you see what happens to the graph, right? Took every point on that graph right there and subtracted 1 from their x value. Okay, subtracted 1 from their x value. And that's much quicker, guys, if I understand that relationship. If I wanted to graph this otherwise, don't I have to start, maybe making a t-chart, say, okay, what is x? If x is 0, what do I get? Plug it in, evaluate. If x is 1, plug it in, evaluate. If x is 2, plug it in, evaluate. X is -1, plug it in, evaluate. X is -2, plug it in, evaluate. X is -3, plug it in, evaluate. And I have to do that evaluation process, however many points I choose. And with a quadratic, maybe I need more than just 2. But if I understand these parent function ordered pairs, if I know them, okay, and then I say, okay, well, if I'm going to add 1 to the x, visually to my graph, all that does is moves all my x's to the left 1 unit. So then I go start with my parent function, x's, and I subtract 1 from them all, and I should get those points there. Okay? Think about, your parent function point. If I put all these on here, we get 0, 0, that was the parent function, 1, 1, 2, 4, -1, 1, -2, 4. And I go find the corresponding position. I'm going to put a vector in here. From there to there. How do I put the vector in? I want a vector 5. So vector 0, 0, 2, 5, 0, 0. There we go. All right, so here's my vector. Okay. If I apply it from there, does it move? So this vector is 5. Would you guys agree that's 5 units long? So I apply it to this point off my parent function, 5 units to there, it puts me on my green graph. Okay, so if I do the same thing then, that point, that vector, puts me 5 units to the right, puts me there. If I go from this point, that vector puts me, that point then goes to there, and we do the same thing, this point with that vector, it froze. That point, using that vector, should take that point and move it to there. Does that kind of make sense? So it's kind of a visual thing that you're doing every single time that you say, okay, start with my parent function, add 5 to each x value. Okay, it's applying that movement to each of those. And if I move those, okay, then all these ones that are in between here get moved accordingly as well, right? Okay, that's why I'm just choosing the ones that are integer x values and y values, because then if I do those correctly, then all these other ones in between get moved appropriately. Questions on that?
No.
Okay. So the thing that they're going to do, guys, is that they're going to give you, because it doesn't matter what the function is, they're going to give you an f of x. They're going to say y equals f of x, and they say, okay, tell us what happens when you do that. Okay? So what's that plus 4 going to do?
Okay, how do you know what you're doing vertical and horizontal?
So it's what you're adding. Remember, this is the rule. F of x is the rule that provides your y value, right? F of x is the rule that provides your y value. If I'm adding 4 to that, that means my y value just increased by 4, right? So when you increase your y value or decrease your y value, that's a movement up and down. So the plus 4 is moving it up. Okay? Now, this f of x is my rule, but this here tells me before you do anything, subtract 3 from your x's and then run that through your function, and then add 4. Okay, so then that means that x minus 3 is actually a movement to the right. So you got to ask yourself, am I doing something to the whole function? The whole f of x, or in this case, the whole f of x minus 3. I'm doing something to the whole function plus 4. That's going to move my y value. If I have to do something to the x before I run it through my function, then I need to realize that that's a horizontal movement. So a specific kind of question like this would be more like, if I have x minus 3 squared plus 4, okay, there you would see that, oh, the x minus 3 says I'm subtracting from the x before I take the power of 2, right? So I'm doing something to an x before I do a more overall function, more governing function here. I have to move, that's a left or right movement. That plus 4 then is what is happening to the y value. I'm adding 4 to those y values. So there, what would happen, if you think back to geometry, we use the notation like this. We use like a capital T, and then down here we would use like a 3 and a 4, and then we would say x comma y or something like that, or a comma b. And basically what it does is it's going to take, if I have this point 0, 0 on x squared, this here and that there are going to move that 0, 0, 3 to the right, and 4 up. And that's going to be my new vertex. So my graph would be something like that. Does that make sense to everybody? And that point there is going to also get moved 3 to the right and 4 up. So maybe that point would be right there. Did a bad job of drawing it, but that's the idea. Okay, now they're going to say, well, it doesn't matter, and that's why they use this notation. It doesn't matter what the function is. So let's go back to this here. It does not matter what the function is. So if I want, right now I'm doing x, I'm doing a power function squared, cubed is going to be the same thing, fourth power is going to be the same thing. But let's do square root of x plus c. Okay? So now as I move the slider to, positive 3, so now I'm adding 3 to my x before I take the square root, right? You see how it moved everything 3 units to the left? Okay? Now, that understanding how the square root operates in regards to your order of operations, maybe a little bit different than the power of 2 does. Let's try this one. Let's go 2 to the x plus c. So now this is a exponential function. We froze. Okay, so there's my parent function 2 to the x. Okay, basically there's 3 points on these that we'll memorize, and we'll have a whole chapter of this. But 0, 1, 1 comma a, which is my base, so 1 comma 2, and then I'll have negative 1 comma 1 over a, which will be this point here, negative 1 comma 1 half. So I'll have 3 points on this. We'll note this is an asymptote here. It's a horizontal asymptote, so that gives me my structure of my graph. Okay, but you see that when I add c to my x, you see where I'm adding to my x in my equation here, right? Okay, well, think about what's happening here. As I go back to this point here, okay, so 1 comma 2 is on this graph. So if I'm going to add 3 to this, it means this point is going to get moved 3 units to the left. So when I put this as a plus 3, I should have a point going through right there where my cursor is. Does that make sense? So let's see if I get that. And that's just by knowing my ordered pairs of my parent function and knowing then when I add something to the x, it's actually going to remove that amount from each of my x values in my parent function. Okay? If you move it, if it becomes minus 3, okay, so we had the point 1, 2, so it becomes minus 3, I should get a point right there where my cursor is. Okay? At 4 comma 2. Is that okay?
Yeah.
Okay. All right, so the last one we'll talk about today is reflecting graphs. Okay, reflecting graphs. Now, there's a lot of little intricate things that happen with reflecting a graph. You're going to see from time to time that when we reflect across the x-axis, that might ultimately look the exact same as if I would have reflected over the y-axis. If that happens, that's a special type of function, okay? Or vice versa, a reflection across the y-axis might look exactly like a reflection over the x-axis. If that happens, it's a special type of function, and we'll talk about that a little bit tomorrow. But what this says, suppose we know that the graph of y equals f of x. So, to generate our y values, we have some rule f of x. Maybe it's x squared, maybe it's square root x, maybe it's x to the third, maybe it's 2 to the x, whatever. We don't care what the rule is. Okay? But it's a way to generate y values. Okay? The next thing says, well, what happens then, or how do you use that to get the graph of y equals the opposite of f of x? Well, if f of x gets me my y values, and then I multiply that entire thing by a negative, what's it do to my y values? It negates them, right? So if I've got like y equals, let's just start with the function y equals x squared. Give me some ordered pairs off of x squared.
That's 49.
Okay. Give me another one.
4. 525.
Okay, so we've got those off of x squared, right? Okay. So this is my x, and this is my rule f of x, which is the y, right? Well, if I say that I'm going to be interested now y equaling the opposite of f of x, something like this. Okay? Well, this is f of x. So what's the opposite of that look like? Negative 49, right? 7 comma negative 49. It'd be 2 comma negative 4. 5 comma negative 25. Okay? So when we see, if we start with y equals f of x, and then they ask us, well, what does this look like? This says your y values are opposite what they were for y equals f of x. So what reflection would that be? It would be across the x-axis. Okay? So, giving us an image of that. All right, so again, just starting with x squared, okay? So if I go, we've got the point 1, 1. Okay, all this does is this will oscillate between 1 and negative 1. That's all that slider does, okay? But you see that if I've got 1x squared, okay, so that's f of x. So that rule, x squared, is generating that y value right there when I know x is 1. Well, when I make that negative, what does it do to that y value? Stays the same amount, just makes it negative, right? Okay, that happens no matter what function you want to look at. Okay, so let's say that I want this thing. Now I have to, in order to type this in, I have to keep that a there, and it probably makes sense. For some reason it hit it, but if you're going to adjust it, you want to go a times, and you see that it's kind of written down here in my notes. But a times square root of x. Okay, well there's my square root of x. Okay, so we know we've got some points on here like 4, 2, flagging. Well, let's just go 2, 1.41. That's it. So 2, square root of 2. If I toggle between 1 and negative 1, there we go. We see that we still have that point 2, 1.41, but now the y value is just negated, right? Okay. Now, here's my question. When we put in, now I don't think there's a cube root. No, they don't. I'd have to look it up, but I don't think there's a command for cube root. So the way I type a cube root in is use the rational exponent concept. So there's your cube root. There's your cube root of x. Okay? Now, as I toggle it to a negative 1, just kind of think about your x-axis reflection. So if it's x-axis reflection, the idea is if I fold on the x-axis, does the stuff that's in the top half plane become the stuff that's in the bottom half plane? Okay? Does everybody understand when I say half plane?
Yeah.
Top half plane is quadrant 1 and 2. Bottom half plane is 3 and 4. Okay? So if I toggle back and forth between 1 and negative 1, did what was up top in the first half plane, become what was in the bottom now? Yeah. Okay? We keep doing that back and forth. You can see visually, fold on the x-axis, fold down on the x-axis, it becomes that, right? Now do me a favor. Fold it on the y-axis. Fold on the y-axis. Does what is in the first quadrant right now show up in the second quadrant? Does what in the third quadrant right now show up in the fourth quadrant? Okay, so this is a particular graph. However you're going to look at it, you can interpret this as having x-axis reflection or y-axis reflection. When that happens, we have two types of symmetry. We have x-axis symmetry and y-axis symmetry. It's a special type of function. Okay, we call this an odd function. Okay, and that has nothing to do right now with numbers or anything like that being even and odd. Odd means ultimately that we have symmetry across the origin, okay, which is equivalent to an x-axis reflection followed by a y-axis reflection, okay, and we'll get into that discussion a little bit tomorrow, but I wanted you guys to see at least an example where it looks like it could be x-axis. This is x-axis reflection because of where I've got the negative, but it could also at the same time look like y-axis reflection, and we'll talk about how we generate algebraically tomorrow, that characteristic, whether we call it even or odd. But we can talk, any function we want to here. We'll put, that would be 2 times a, not times, 2 a times x. We do something like that, okay? So now you see, okay, I'm multiplying this one. What am I multiplying by a negative? Am I multiplying the entire function by a negative? No, I'm multiplying the x value by a negative, right? So you're going to choose, so here's the idea. In order to graph something like this, you would choose some independent x value, whatever you want it to be, But before you took it and raised it as the power for 2, you would negate it. So if I chose -1, I would actually negate -1 first. So I'm choosing -1, negate it, it becomes 1. Now you can take 2 and raise it to the first power. Wasn't it give me a y value 2? Okay. But a negation of the x, what axis does that look like we're flipping across? Yeah, if I started that and I fold the y-axis, doesn't it become that? Okay. So that's the idea here. If I take the entire function and multiply it by a negative out front, it's going to be an x-axis reflection. Okay. They call that a vertical reflection because the graph moves in a vertical fashion. Does that make sense? If I look at just so we know terminology, because you're going to hear this. I go back to a times x squared. Would you agree that the graph is kind of moving vertical? Does that make sense? So they call it a vertical reflection. Okay. If we look at, let's just do this one. Let's go a x minus 4 squared, something like that. So there's that function. So x minus 4 squared is kind of my parent function here. You see how if I toggle back and forth between the negative here, it's still vertical, right? Okay. But if I put the a right here, so I multiply the x by a negative, you see how that's a horizontal reflection? Yeah. Okay, because the movement of the parabola is horizontal. But you see then that what is getting changed? Now this negative is being multiplied by the x first. You are then subtracting 4, and then you're going to run it through the entire function. So the order of operations dictates horizontal or vertical movement. I'm going to stop there with examples, but I want to show you something real quick on my website that I think is going to be beneficial for you to start learning now. So there's two overall tasks that we're going to be asked to do with transformations. One will be just to gain the information from a function. So I might give you something like, let's say, f of x equals, maybe I'll go -2x plus 3 to the third minus 4. The first thing I'll ask you, what's the parent function? What's the most simplistic version of this function? And we should see that it's x cubed. Okay, does that make sense? Okay. Then I'm going to ask you, well, what's that negative out front do? What's that -2 do? Tomorrow we'll talk about what the 2 does, but it stretches your y value. Makes your y value twice as big. Okay, but the negative in front of that, I'm multiplying the whole thing by a negative. Does that make sense? So a negative out front is an x-axis reflection. So I'll ask you that. The +3 on the inside, what's that +3 do? Moves it left 3. What's the -4 do? Moves it down 4. If you can collect that information, and it doesn't matter the order that you collect it, but you can collect all that information. An x-axis reflection, you've got a stretch vertically of 2, a movement of left 3, and a movement down 4. You write that stuff down. Then you start with your x cubed ordered pairs, and you do that to each ordered pair. You should get your graph. Okay? Now, the one thing that happens is that when you have a vertical translation and a reflection together, and so here's the idea: is that a vertical translation, how can I phrase it? No, let's do this. A reflection is dependent on a vertical translation. So in order to remove that dependency, if we do the reflection first, we don't have to worry about the dependency. Okay? And I'll show you an example of this tomorrow. But it's the idea that when I do a vertical translation, every time that I move it up or down, I'm actually moving the axes of reflection with it. Okay? And I need to understand that, because if I'm going to do a reflection after I do a vertical translation, I'm no longer reflecting across the x-axis, but I'd be, in this case, if I did the vertical translation of -4 first, I'd actually be reflecting across the line y equals -4 instead of the x-axis, okay? And that's something to be cautious of. If you use this setup right here, you'll never go wrong. You'll never graph it incorrectly based on your reflections and translations occurring together. The way I remember it is just grab these first letters, HSRV. You can remember HSRV in that order. You'll always be right in graphing things. There are some assignments open due later in the week.